Ladies and gentlemen, my name's Paul, and in this RedGamingTech.com video, we're going to be discussing as well as analysing tech news which, as usual, has popped up in the past 24 or so hours. Hopefully, you're having an amazing day. We have lots of news to get through in this particular video. I'm going to start things out, though, with a smaller thing from AMD, and it concerns the IPC improvement for the Zen 3 microprocessor architecture, which, of course, will be part and parcel of the Ryzen 4000 series, which looks like it's going to launch later this year. And I actually would like to thank David on Twitter for discovering this. It was originally posted on Weibo.com. Now, this information is unverified, so I want you to proceed with lots of salt on hand. But I can say that I have heard from numerous people, and I actually put out a couple of videos regarding Zen 3's IPC myself, that we are going to be looking at around 15 to 17% on average for the jump between Zen 2 to Zen 3. Now, to be clear here, this will of course be dependent upon the workload. Some workloads will see a larger leap, other workloads will not see such a great improvement. But as I mentioned, the top end I've heard is around 17%. But the lower end I've heard is, low teens, 12, 13-ish percent, something like that. But anyway, getting back to this particular topic, the individual who's posting here claims that Ryzen 4th generation will be a pretty big leap over Intel, not only in terms of performance, but also power consumption. According to what has been posted, the 15 to 17% IPC gain that I spoke about actually may no longer be accurate, because according to engineers who are working on this project, the actual final performance of the Zen 3 architecture could be above that, which would be kind of bonkers. What I can say is officially AMD multiple times have said that Zen 3 is not going to be a small iteration. It's not going to be a small performance bump like we saw from Zen to Zen Plus, which obviously, yes, did have small IPC gains, 2 to 3%, but really was more of a clock frequency bump, albeit not exactly a vast one, and also improved cache as well. One of the reasons that Zen 2 was such a big leap is because Zen 2 actually had some features which were originally intended to be in Zen/Zen Plus, but they just didn't make it in time, and therefore Zen 2 was kind of like a collection of fixes which were originally intended to be in the Zen debut architecture, plus also the natural leap of moving to a different architecture anyway. Just as a quick reminder though, the number of processor cores for the next generation is going to be identical. So it's still going to be up to 16 cores for the what I assume will be called the 4950X. There will still only be 2 threads, or up to 2 threads per core. And also, you will need a 500 series board to take advantage of Zen 3. So in short, if you have, let's say, an X370 board or a B450 board, you will not be able to use that for the Ryzen 4000 series, and this has been officially confirmed by AMD. I'd also like to move on to Unreal Engine, and I know that typically I cover topics alphabetically, but I couldn't really wait. I really wanted to talk about this, so here we go. But as most of the internet at this point is aware, Unreal Engine 5 was demoed yesterday on a PlayStation 5 development kit. And I will be going much more extensively into this over the next week or so. I'm not exactly certain. It will be soonish. But honestly, I want to kind of make it a part of a larger project on next generation graphics that I'm working on. This was actually spurred on by a couple of articles, which I won't name, that have been floating around the internet, basically saying that the next generation won't be a large leap in visual performance and quality, and I really don't subscribe to that point of view. So a number of you actually asked my opinions of this, so it kind of spurred this on, and it works out extremely well, because of Nvidia's next generation GPUs, which we'll talk about in just a moment, as well as Unreal Engine 5 and some other technology, which I think is going to be of paramount, of critical importance to delivering unprecedented visuals on the next generation of PC games, yes, but obviously this stuff is also going to scale on to console. But getting onto the PC side of the equation, PC Gamer heard from the Chief Technology Officer over at Epic, and they said that an RTX 2070 supercard could run the Unreal Engine 5 demo at, quote, a pretty good performance. Obviously, the big difference, the big disparity between PC and console hardware is that the next generation of consoles have SSDs as standard. And I think that that really is going to be a very interesting problem for games developers to solve. I mentioned this in a previous video regarding how PCs will most likely need to evolve given console hardware, and basically there are multiple solutions. The first is that NVMe SSDs become the norm, because SATA just does not have the throughput necessary. The other option is that we simply see a drastic increase in the amount of RAM which is required to run next generation games. I also suspect as these visuals become pretty normal, it's going to really start to hammer the PCIe system of a PC. So in short, if you've only got like a ×8 PCIe free slot, that might be a bit of a problem for games soon, because right now, to be honest, a lot of titles don't really have that much of a frame rate drop if you put them even in a PCIe 2 slot. If you have, let's say, a 9900K, feel free to test this. Like, over a couple of different resolutions, check a couple of game benchmarks with the default speed of like ×16 PCIe 3, then drop into BIOS and then drop it to like a PCIe 2 speed. And yes, there is a subtle drop in performance, but it's not absolutely monumental. And now let's move over to Nvidia, because the company have finally provided details on Ampere. And I will spoil it for you right off the get-go. It is absolutely disgusting how powerful this darn thing is. Before we get into the architecture though, there is something that I do want to get out of the way, and that is that the actual Ampere architecture is not just for high-performance computing. I will read this verbatim. This is according to Jensen himself, who was speaking to MarketWatch. Ampere will eventually replace Nvidia's Turing and Volta chips with a single platform that streamlines Nvidia's GPU lineup. This was in a pre-briefing with media, by the way. And unquestionably, it's the first time we've unified the acceleration workloads of the entire data center into a single platform. Unfortunately, Jensen, unsurprisingly, was not too willing to give information as to exactly what we would see with gaming variants of Ampere. He simply said that there's a great deal of overlap in terms of the architecture, but the configuration is different. If I had to speculate, that's probably HBM2 out of the window. I'll get into the specs in just a moment, just for a start. And obviously there'll be differences, most likely in like FP16 or FP64 performance. And, well, actually, let's just get into the specs. My decision on how to handle this is to go kind of an overview approach, because we still don't know about the gaming derivatives, which I figure most of you are interested in over the high-performance computing side of the equation. But I do want to tackle at least some of this stuff, because quite frankly, some of it is really interesting for the gaming side of the equation as well. So I want to go over some of the things that I find most interesting, some of the specifications for the GA100 architecture, and then overall I'll kind of end with my opinions. So as for Ampere, the A100 is the Ampere architecture, unsurprisingly, which is comprised of 54 billion, repeat that again, 54 billion transistors, which makes it the largest 7nm processor that is available or will be available. We also have third generation tensor cores with TF32. Now, tensor cores are very important in the data center for inference training and AI in general, but they are also going to be of critical importance for gaming. One section of the keynote was actually Jensen doubling down on DLSS2, which of course is Nvidia's AI upsampling, and they were really pushing the fact that DLSS2 is a drastic improvement over DLSS1. It looks like Nvidia are going to continue to push that as heavily as possible because it's going to be of critical importance for hardware-based ray tracing. And my opinion is that titles will be a lot more common in using DLSS as well, as we're seeing the neural networks from Nvidia become a lot more generic and a lot quicker to train. So I suspect that there's a very good chance most new AAA titles in a year or so will be DLSS2 compliant, assuming they don't move on to DLSS3 or something by that point. Anyway, I guess the point I'm trying to make is this is really good in terms of cost/performance, as you could pick up, let's say, a 3060 or something like that for a reasonable price and still get pretty damn good performance, especially if it's rendering internally at like 720p and obviously upsampling. But as for the third generation, well, it's pretty darn impressive because assuming the developer does not change any of the code, which is definitely good, obviously, if you're a developer working on neural networks, the Tensor Core third generation actually supports TF32 specifically for AI. And this actually allows up to 20 times the AI performance. And this, once again, just to be really clear, is without any code changes at all. Furthermore, the tensor cores can support FP64, which is over 2.5 times the performance for high-performance computing applications. Now, as we know, DLSS runs on the tensor cores, so you can make your own predictions with all of that extra computational grunt at the disposal of DLSS. What could potentially be done? The accuracy could probably be even higher. After all, DLSS 1 to DLSS 2, in terms of performance, there wasn't that much of a difference. It's a frame here, a frame there, but honestly, pretty interchangeable. But the accuracy is so much higher. So imagine what can be done with games in the future. Oh, by the way, I did cover this rather extensively with DLSS 2 in a separate video. I'll try to remember to link it in the video description. This one is something that is purely for the data center, really, but it's called MIG. And it basically enables a single GPU to be partitioned to up to 7 virtual GPUs. So in short, this is great for data centers, servers, because let's say you have a couple of customers who don't need all of that performance, then they could basically just choose the amount of computing performance they need, and then that GPU can then be divided up between them. And obviously that's really good for bringing the cost down of cloud. But even if you own your own system and you've got several researchers working on projects, then you don't need to worry so much because that GPU or those GPUs can be used however the projects would naturally flow. So if, for example, one researcher or a couple of researchers have something that's kind of easier to do and they can just quickly do that and it might only take a couple of hours to run, they don't need so much GPU might, whereas perhaps another team are working on something a lot more complicated. And all of this, of course, is just a means to provide additional flexibility. I should have also mentioned, along with the tensor core, I forgot, sorry, that we also have structural sparsity, which is also going to be a really big thing for AI. Basically, if you have AI code running, you could double the performance, and this is just basically because AI math/code typically can be rather sparse in terms of nature. So that could be almost like a free performance win. There are other things which we see with the Ampere architecture, such as third generation NVLink, which is a drastic increase in the amount of bandwidth, which allows obviously different GPUs to communicate with one another. Okay, so now that I've gone over some of the basic features, what about the actual architecture? Well, A100, GA100, is absolutely monstrous in terms of complexity. The full implementation of GA100 is the following. We're looking at 128 SMs per full GPU with 64 cores inside each. So the full implementation could have up to 8,192 FP32 CUDA cores, 4th generation tensor cores, and there are also 4 tensor cores per SM, and this is accompanied with 6 HBM2 stacks. However, the GA100 silicon is not the full implementation, so we are looking at only, he says, 6,912 CUDA cores and 5 stacks of HBM2. You can see this breakdown table of how the different generations of Nvidia GPUs, P100, V100, and of course A100 all compare against one another. One of the big, I guess you could say, reductions here would be clock frequency. You're looking at 120 megahertz lower boost frequency, though of course that doesn't necessarily translate to gaming because it's going to be radically different. As for one of the biggest changes, level 2 cache, because it's 7 times or almost 7 times larger compared to what we have with Volta. Although, honestly, memory bandwidth and cache sizes have just gone up across the board. For example, the HBM2 bandwidth for Ampere is 1.6 terabytes per second. Compare that to a paltry 900 gigabytes per second with Volta. As I mentioned, almost 7 times the amount of level 2 cache, but also the amount of memory per SM has also been drastically increased as well. The shared memory size per SM has risen from 96 kilobytes up to 164 kilobytes. As for the TDP, this thing is 400 watts, which is certainly not exactly low power, but obviously with the usage scenario this is intended for high performance computing, that makes a great deal of sense. The GPU is absolutely ridiculous in size as well. It's 826 squared, and once again is being fabricated on TSMC's 7nm N7 process. I will be extremely interested what Nvidia does with the gaming variants of the Ampere lineup. I guess we're probably going to hear about those in a couple of months. I assume there's probably going to be some leaks starting to emerge. And clearly, the market conditions they're going to face are going to be very interesting. AMD will be putting out the RDNA 2 GPUs, as we all know, but furthermore, they're also going to be fighting off against consoles, which is one of the reasons that I suspect DLSS is going to be so important, as it's quite difficult to put out what essentially would be an entry-level card and charge several $100 US for it. And obviously that was one of the big criticisms of, let's say, the RTX 2060. And interestingly enough, Jensen himself admitted that they did not get certain technology for Turing correct. But I think it's going to be very interesting because not only will Nvidia be fighting off RDNA 2, but also next generation consoles too. And given the supposed price point of the next generation systems is going to be $400 to $500, it's going to make, I think, mid-range cards for PC very interesting, especially if you've got a decent-ish CPU. If you've got something like a 2700X or an 8700K or faster, obviously preferably faster, and you pair that with an RTX 3070, assuming that's what the cards end up being called, I think we're going to be looking at an insane amount of performance. But as always, we can only wait for official confirmation. With all of that said though, hopefully you've enjoyed the video, the normal stuff. If you did, like, share, comment and subscribe. I'm working on several very interesting projects in the background, so hopefully you will stick with me for when I actually upload those. But for now, I'm going to let you all go. Take care of yourselves. Bye for now.